panels, everybody's seen them on the front of the building. Combiner box is stuck right up on the side of this sky vent up on the roof. So,
why is it up there?
because it has to be up
Close.
there, outside.
Close to the panels?
Yeah, close to the panels for one. And the other is, it's just a good location as compared to coming in the building.
Right.
So normally, if we've got the power system, the battery box up on the roof, it just goes right on the outside of that and then drops straight into the building. So the strings of panels come together in the middle and come into the combiner. Here, rather than putting it up on one of these other boxes and running conduit through the entire greenhouse and all the rest of that, it came into here, came in on this 1-inch conduit right here. So anytime the solar electric comes inside the building, it's got to be in a metal conduit or a metal raceway. So comes in here, and this is the load center here. So comes into the load center into a disconnect. Number 3 PVN right here. Goes out to the charge controller. Charge controller's here. Right now we're at 26.3 volts.
0 watts.
57 watts coming in.
Just 0 like 10 minutes.
And 2.2 amps. Charging the shit out of it right now. Not really. But we're at 26 volts, we're good.
Don't touch it.
So comes in, through a breaker, out to the charge controller output, then goes through another breaker and ties into the DC side through a bus bar. So this is why I don't have a wiring diagram of the load center.
It's not too bad.
No, it's not too bad, but you know.
Professional.
So basically, there is a diagram here on the lid or the cover. So I could hand one of those out as well, but you know, most people look at that pile of lines and you know, it's just going to add to any sort of confusion.
I agree.
So inside of here, we got our battery cables here, our big 4-aught cables coming to our 250 amp breaker and up to the inverter. There's also common bus bars down here. So one of them labeled DC negative, that hooks up to the negative side of the DC, just so you can make multiple connections in there. So the charge controller comes down into one of those. There's a line out from there that goes to the DC breaker box here. And there's also one for the positive side. So you can see over here, there's a common grounding bus bar to make all the DC box and the AC box and the solar panels, gives them a common connection that ties into this big fat cable here, runs down and ties into our UFA ground there on that piece of rebar that runs through a footing that supports, you know, all these posts and this beam running across the garage here. So there's that.
Do you need to have all that S-play in the ground cable?
As far as the slack that's in here, no, it's just made for easier routing. Just you know, having some slack in there to clamp it on. This is all eventually getting enclosed in a big cabinet, so you won't even see any of this. So anyway, the common DC positive and negative connections, the common ground connection for the system. This again has gotten covered in a bunch of stuff. The batteries are housed in here. So battery to battery connections are made in there. The 2 banks of batteries are connected together in parallel to get our storage capacity there. They run through these big 4-aught cables. Breaker here, 250 amps, will interrupt the supply to the inverter. And you get the negative one here, goes up to a shunt, and then pulls off of there for a common connection down here for the DC negative, and then up to the inverter. So red and black are positive and negative DC connections to the inverter here. These breakers here are a control for two things. One, if we had a generator, shore power, grid backup,
That can be good.
it would run through one of these breakers. The other,
This is the DC breaker, right?
this is the AC side
Oh, yeah, that's what I mean.
coming out of the coming out of the inverter here. So the inverter makes the AC. So we get it set up in the future to have AC in, come through a conduit, feed this, or the AC out, then comes through the other conduit. You've got your first disconnect here, your main breaker at 60 amps. Then it runs to the AC box over here. So there's DC box. You see reds, blacks, and greens in there. 15 amp breakers on everything. It's all labeled down here. One goes to the fridge. One's the WOM. One is the one half of the greenhouse lights. The other is the other half of the greenhouse lights. And the other one is our gray water board over here that'll pump gray water and flush the toilet.
Kris, when you connect them, do you do like one wire at a time and then bring it back here, or how do you?
Well, the conduits here are what's carrying the wires. So you just pull like one conduit worth, whether it's got one circuit, 3 circuits, whatever, different runs in it, and ground with that. So here is the AC side of things. If I can get the damn thing open. So the system is shut off right now. We turned off the main DC breaker. So we have no AC happening in the inverter. So there is our AC side. So yes, there's red wires in there. You won't worry about that. That's still a positive. Or you're hot. So there it is, all labeled up. All the common grounding in here, which runs through, ties to the main ground here. Same thing over here, common grounding, ties into the main grounding there. With bus bar, all your, just like we did in lab with the single connections, this is how it's done in the bigger boxes. All your neutral connections here, and all your positives or your hots are gonna run through breakers.
Are those specific to the breakers, or can you just throw them in anywhere? The neutral.
Those are all just a common connection.
They're
So
specific on the FCI.
yeah, on the arc fault here, which are required by code, specific to each one of these circuits. That
Breaker
those
will
are
have a
hooked up
white
to.
wire on it.
Yeah. You can see it right here on this one, and this little pigtail that goes up and ties in there. So just like what we did in lab, but a lot more, basically. So the main that comes in here from our AC output breaker or disconnect here. And then you can see on the DC side as well, these bigger number 6 wires here that run in to their individual breakers and make their connections there. This guy here, the sun's coming up, awesome. This is for the gray water recirc on that little panel on this end of the building. It just comes in, goes to this voltage regulator here, and then just passes through this box into one of these conduits and ends up over there. And also the supply for the DC pump for the toilet or gray water pump also goes over there. So
And you run that on DC, so if the inverter's fucked, you're still good.
you can still flush your toilet. And the reason we're doing the pump on its own dedicated panel is you don't have to think about it, you don't have to turn a timer, you don't have to flip a switch. As long as the sun's out, it's recirculating gray water. It's been running for the last 2.5 months. If you look at the housing over there and how clear that water is, that's what the gray water looks like right now. Because we've been recirculating in there. There's no plants to help clean it out. Awesome. But it is you know, it's normally we have to wait when we'll flush initially on fresh water because the gray water hasn't been cleaned and established quite yet. So I tried it out here. Hey, what if we start recircling as soon as possible? That way we can hook the toilet up straight away on gray water and not have to waste any fresh at all, flush and turd and whatnot. So
But the battery only gets connected to the inverter, right?
well, there's also common connections down here. So there's a DC negative bus bar and a positive connection here for the DC. So you got two common connections. So to supply the DC breaker box, you run through a breaker for a disconnect and overcurrent protection, and then it runs into this box for the DC supply. So the DC does run off of the battery power directly.
But basically, when you install it, the system, the battery goes directly to that apparatus.
Yeah, to the load center here.
Oh, load center.
Yeah.
Why not
So
think
this
of an
is the load center, the actual wiring and guts inside of it. As I said before, too, different brands, different layouts. This one's nice because we can put our own components into it. Other brands sell, turnkey units that have got everything in it. Outback Power Systems makes one. The new Schneider Electric that used to be Xantrex, that used to be Trace, has their own type. This Magnum, actually, if we were running a Magnum inverter, it would stack right on top of it and wire directly in here instead of having to run around to here and the rest of it. So over here, and there's a lightning arrestor up on the combiner box up on the roof. All right, 1,300 watts now. This one's just in here for the AC side in case something happens and there's a surge in the system. These typically don't surge. Like you can get a surge in the grid and things like that. You use your surge protector strips. But that's in there just in case. Some of the other inverters and different brands and things like that have these built into the system for surge protection only, not for lightning protection. They will help if you don't have a lightning arrestor, but ideally you should have one up there in the box. So this one's just tying into the AC side here to protect that. So yeah, and you can see here conduits running down on both the AC and the DC side, and they go into the wall here and run the length of the house and basically, go off to where you need to. What's that? The 12 minutes lost. Big units. So that's basically this portion of the system. Any other questions?
I know that this what is it? Not the surge protector,
Lightning arrestor?
no, the one that dissipates the extra energy is heat.
Oh, up here.
What's that called again?
This
Charge
is a charge
controller.
controller, and that's a heat sink
Alright.
on there.
Does a charge controller send extra energy to directly to your refrigerator and
Some models can be set up that way with what's called a diversion load or a dump load. We used to run the gray water recirc on that, so when the batteries got full during the day, it recirced. But one of the downsides there is if you're at home more and your system never gets fully charged to float, or it only does for a short period out of the day, your gray water only recirculates during that time. So this one, you can put a diversion load on. It takes extra equipment. Basically, you gotta have this little, almost like a router type box and relays and things like that. So this is just set up to turn that excess electricity basically into heat energy. through this heat
So
sink.
I mean, really, you shouldn't have that much
Yeah.
excess electricity. I mean, this
Yes.
thing's
If the
doing
system
the math
size,
to get as much power into your system.
yeah. So if you size it correctly, you know, you shouldn't be producing a large excess.
They used to have to do dump loads basically because
Yeah.
they had no other way to get rid of all the power.
Yeah.
But now these charge controllers can like handle all that extra power.
Yeah. Like right
You
now,
could heat water with a dump load. You can do all
you can recirc, you can run an anti fan, you can run a fountain out in the yard, do whatever you want with it, pretty much, as long as it's.
But it's just easier just to dissipate it as heat and have
Yeah,
all that
exactly.
other
I
stuff
would
on top.
not probably, unless you want to geek out on something, probably I would not fuck around with the
So yeah, right now we've got batteries are at 28.7. It's coming up here until it stabilizes. So 1130 watts coming in, and this is turning some of that voltage coming in from the panels into amperage to charge at 35.9. So we got 3 strings up there. They're in series. Each 3 panels is only producing 8 amps maximum between the 3 of them. So we got 24 total. So what's going on is this charge controller is taking some of that voltage and basically converting it to amperage to charge. So now we're up to 32 amps. We drop down to 977 watts. So basically, it's just doing the thinking. It's monitoring everything that's going on, and it's like, what's the best way to charge right now? Amps or volts, or half and half. So this is going to put out a maximum of 60 amps to charge with, if necessary. And right now, it's putting out half of that. So basically, so yeah, now we're up to 1,073, 71 watts, 67. And it's just, you know, monitoring every few seconds what's going on with the input side and what's going on with the battery voltage. So some of them will do it, you know, some of the more expensive ones, more bells and whistles and things, do it a few times a second, you know, to totally optimize what's coming in. But yeah, we just bumped up to 40 amps and almost 1,200 watts coming in right now. So it's constantly adjusting what's coming in to charge the best way possible. So now we're dropping off again. You know, we get some cloud cover. Sun's going in and out of that, and it's just figuring it out. So now we're back down to 31 amps and 902 watts. So it's just sitting there. I mean, this is actually a good time to be seeing this thing doing what it's doing because we've got so much variable conditions going on outside. We had full sun a minute ago, partial cloud cover, thicker cloud cover moving in and out, and it's just doing what it does, controlling the charge.
So what's the difference in it controlling the charge in volts or amps?
So it has different modes on how it charges. Right now it's in an MPPT mode, so it's basically sort of taking what's available and using like half and half voltage amperage. Because the max output is 60, it could take this 1,000 watts and turn that into 60 amps if it needed to. What it's going to do in the morning on like bulk phase is it's going to start with a lot more charge. Because first thing in the morning, you use stored energy in the batteries all night. You brought it down to 24, 24.5, something like that. So first thing in the morning, it's going to push more amperage to get this charge started right away. And then as it transitions from bulk, so it's dropping the amperage off, letting some more of the voltage in. As it transitions to MPPT mode, where it is now, so now we're up to almost 1,200 watts and 40 amps coming in. And MPPT mode is just going to figure out what's better, voltage or amperage, or a little bit of both to charge in the most efficient manner. once it gets up to close to where it's at right now, so 28 to 30 volts, depending on the model, or if there's manual settings on it, it'll go into float mode. So it'll just sort of trickle in kind of like it was earlier when there was not a lot of sun. It'll push 20, 30, 60 watts into it. And just a little bit of voltage or a little bit of amperage usually, just to keep it, the battery's topped off basically. So they've gotten to the point where they're full, and they've gotten just past full on more of a surface charge, then it drops down. It's sort of, all right, what's going on? A little amperage, a little voltage, something like that. And then, so if we just plugged a bunch of stuff in, shop saws, table saws, whatever, and put a bigger draw on the system, you're going to see it drop. And, the charge controller may throw more voltage into it or more amperage right now, just to compensate for that usage when it's close to its full float stage. So, this is sort of the brains of the operation right here. Does all the thinking. The rest of this is all just, mechanical breakers and things like that. So, this is where that happens. This as well doesn't really do any thinking. It's a pretty simple model. Some of them will. But again, this thing, 4,500 watts continuous output. It'll double to 9,000 watts for 30 minutes and triple to, 13,500 watts for 30 seconds. So, if, you need a lot of startup, because most things, even table saws, chop saws, to start up, it takes more electricity than it does to just run. Or if you're cutting on the table saw and you hit a knot and you can hear the saw bog down, then it's going to pull more to get through that task and sort of